Okay, so here's our geometry section. We're starting in 10.1. We're talking about points, lines, planes, and angles. There's just some algebra and some definitions. So there are a few things to memorize. There's a few things from algebra that you have to apply. It's a pretty straightforward section, I hope you'll find. Okay, so we want to talk about our objectives. We just have 3 for this particular video. We want to understand points, lines, and planes as the basis of geometry. We're going to refer back to these 3 objects quite a bit. We're going to solve some problems involving angle measures, right? And then we're going to solve some problems involving angles formed by parallel lines and transversals, and just talk about some of those properties. Okay. Now the point, I told you we were going to talk about points, lines, and planes. So the point is represented as a small dot. In mathematics, it has no length, width, or thickness. So even though this dot right here does have some dimensions to it, for us, we're going to consider this a dimensionless object with no length, width, or thickness. Okay, and then a line connecting 2 points, right, along the shortest path. And it, of course, has no thickness, but it has an infinite length, right? So here are 2 points. You got a point right here and a point right here. I'm going to connect these through a straight line, the shortest distance between the 2 points. And you'll notice the arrows on the end imply that this extends on forever, okay? So when you terminate in a point, it doesn't extend on forever. When you terminate in an arrow, it does. And then last but certainly not least, we have the plane. The plane is a flat surface. I know it seems kind of weird. We're using plane and surface, but basically it's 2 dimensions. It has length and width, but it has no thickness and it has no boundaries, right? So it has length going up this way. It has width going this way. It incorporates all of the surface inside. But again, these arrows imply that the boundary extends on forever and ever. So there's actually no boundary to a mathematical plane. Okay? Again, just some more definitions as we become more and more acquainted with their properties and trying to do something with it. So a line may be named using any 2 of its points. A half line is formed when a point divides a line, and not in half, okay? That you may interpret this to mean in half, but it just divides it into 2 pieces. One end that doesn't extend on forever, and the other that does. All right? A ray is a half line with its endpoint included. So there's a nice distinction here, and I want to sort of point it out. A half line does not include the endpoint. And so because it does not include the endpoint, it's going to have the open dot and the arrow extending, right? So remember, the open dot from algebra means that this point is not included, whereas a ray is a half line with its endpoint included. So I'm going to shade that endpoint in and include that as part of the thing. Now, this, not very common. This, pretty common. Okay? And, of course, a line segment is a portion of a line joining 2 points. Okay? So now this is finite. Got an endpoint here, got another point over here, and I connect them. Alright? So a line doesn't have any sort of ending. It's infinite. Okay. The half line is infinite in one direction and doesn't include the endpoint in the other direction. A ray is infinite in one direction and includes the other endpoint. And a segment has 2 endpoints and is finite. So this one is the finite one of the group. Okay. Now there are several ways of representing these in mathematics with pictures, which is what we typically do in geometry. And so here we go. Right? In the diagrams below, A closed circle indicates that the point is included, right? So this is our segments or our rays. An open circle indicates that the point is not included. So A and B create the line AB, and you'll notice the line symbol above the two terms. So this is the definition of a line with the little segment on top. Here you have the open dot and the ray coming off of it. So this is going to be a half line AB because A and B are part of it. And look, there's the half line symbol that I drew on the previous slide. Here's your ray, including the endpoint. And of course, then we just don't make an endpoint distinction. We just show the ray of AB. And for a line segment AB, it's just that line over the top, showing that it terminates. Alright, so pretty much what the object looks like, open-ended, there's the two arrows, open in the arrow, closed in the arrow, just the arrow, and then the two endpoints, and so you just have a segment with no arrows on the top. So it's pretty straightforward, okay? Now, yeah, so I've changed my mind. I wanted to go back to this particular slide. Now, if you've got a line here, right? Okay, let's say you've got a line here, and you've got A, B, and C on it. Excuse me. You could write AB, and there's your line. That would be the line AB. You could actually write BA, and you could write the ray, right? And so that means the ray terminates at B and extends off in the direction of A. All right, so that would be one thing. You could also write AC, right? The line AC, because those are also points on the line. And of course, you could just write the segment BC, and you would just be talking about this part of the line segment right there. Maybe I care just about that. So the lettering is important for the endpoints, and the symbol on top is really important to let you know what you've got. So you could have a much larger object with different objects that you're describing below it, depending upon your needs. And that makes us happy because we've got some flexibility here. Okay. Now, what do we do with two lines, right? Well, we use two lines to make angles. So we're getting into new territory here, right? So now we're going to talk about angles. So an angle is formed by the union of two rays. Okay, one ray is called the initial side, and the other ray is called the terminal side. There's a bit of debate about which one is which. Hopefully in my math lab it tells you. But usually the initial side is where you're going to start, if that's clear, and the terminal side is where you end up, if that's clear. Okay, now this one says ABC, so I'm going to say that AB is probably the initial side, okay, and BC, the ray BC, is the terminal side, because, you know, A and B start the alphabet and B and C are next, okay? So that's probably just what I would call it. The vertex is right here in the middle. It's the common endpoint. Common endpoint. Okay. And that's pretty much it. Okay. So this is the angle measure between the two rays. So this is the angle between the rays. And I guess there's really a couple of ways of doing it, but I guess what they want you to notice here is that the vertex is always in the middle. Okay? Excellent. Now, that's how we look at rays. Those are their pieces. Now, what are some other things that we can do with them? Well, we can measure the angles using degrees, and angles are measured by the amount of rotation from the initial side to the terminal side. So, again, this is where you're going to start the angle on that initial side, and the terminal side is where you're going to end the angle, okay, on that terminal side. Angles are measured in degrees and symbolized by that little superscript open dot. There are 360 degrees in a full rotation of a circle, and so 1 degree is 1/360th of a complete rotation as you go around. So of course there's 360 degrees in a circle, and so 1 degree is 1/360th of that complete circle. Okay, and so this makes us pretty happy because it's straightforward. All right, should be fairly familiar. So now we've got the hour hand of a clock moves from 12 to 2 o'clock. Through how many degrees does it move? Well, our initial side is up here at 12, right? And our terminal side is over here at 2 because it says it moved over to 2 o'clock. And what I'm trying to ascertain is the angle measure in between here. And so I'm going to use the Greek letter theta, because theta is what they normally use as the variable for an angle. So those of you who are, other places and watching this for other classes, I want to be real consistent with the mathematical nomenclature. Okay, and so this is my angle measure. Now, there's a couple of ways of doing this, but I'm thinking probably the easiest thing to do is, because the clock is divided up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sections, right? I'm basically going to take 360 degrees and divide it by 12. Okay, and that's going to give you 30 degrees for each one of these sections right here. So this right here is 30 degrees, right? This right here is 30 degrees. This here is 30 degrees. I've got 30 degrees all the way around, okay? And so I can see there's two 30-degree angles there, a 30 from 12 o'clock to 1 o'clock, another 30 degrees from 1 o'clock to 2 o'clock, and so I get 60 degrees total. And so theta, the angle made between 12 o'clock and 2 o'clock, is going to be equal to 60 degrees. Alright, and that makes us happy. Okay, now you can do that with any angle measure here. These should all be in degrees. Okay, so that's how you would use a clock. Alright, now we're also going to use the clock to define a couple of special types of angles. Okay, we've given the pieces, we've learned how to measure them, sort of. And so now we're going to look at some of the special angles. Now, if you grew up here in the United States, I know that in K through 12 we go over this. I'm guessing most other countries probably do too. So acute angle is probably going to be very familiar to you as less than 90 degrees, less than a right angle. Okay, and so a right angle forms a perpendicular set, and so an acute angle is smaller than that. And acute is Latin for sharp. Okay, so it's a sharp angle, and that's because it's so small. If you look, that comes to a nice point there, and so this is a sharp angle or an acute angle. The right angle is perpendicular. Okay, so the right angle is perpendicular. It's at a 90-degree angle. All right, the obtuse angle, obtuse actually means thick. So as opposed to a sharp angle, which is very small, this is a thick angle where you're greater than 90 degrees but less than 180. And that's really important to sort of distinguish it from. So it's more than 90 but less than 180. So I'm in this range over here, and you can see it's a very thick angle, very slight deflection here, and so it's obtuse. And then the last thing that we have is when you're actually equal to 180 degrees, you have a line, because now you've cut the circle in half, and so half of the measure is on one side and half is on the other side, and a straight angle gives you a line. Alright, so every line has 180 degrees in it by this definition. Alright, so acute is sharp, a sharp angle. Right is perpendicular. Obtuse is a thick angle past 90 degrees, and a straight angle is equal to 180, and that forms the basis for our line and its measurement. Okay. Now, I know some of you are education majors, and you're going to have to teach this, and you're going to be using hands-on manipulatives. And the way that we measure things in the real world and in our geometry classes is with a protractor. Right? And so protractors are used for finding the degree measure of an angle. They're pre-measured, so that gives us some confidence there. We measure the angle by placing the center point of the protractor on the vertex of the angle and the straight side of the protractor along one side of the angle. We read the degree by reading where the other side of the angle intercepts the edge of the protractor. Okay, so what this is basically saying is, and I'm actually going to go ahead and sort of zoom in here, right, on our protractor. You put the vertex in the center. You line it up along the initial side so that it starts out at 0 degrees, and 0 degrees is always going to be over here. And then you follow over until it crosses. Okay? Now, this is an acute angle. It's less than 180 degrees. So you're going to read the inside edge, and this is going to be 50 degrees. Okay? Now, if you were going to go out, right? If you were going to go out this way with it, okay? Now the initial side is over here, the terminal side is over here. This is an obtuse angle, all right? So I'm still going to read this inside edge where I have the 120, okay? Because I started from 0 and I'm going through each of these over this way, and so I'm going to be at 120 degrees over here. The only time you would use the outside is if the initial angle started here. That's the only time you're going to use the outside, all right? So that's going to give us a good basis. That looks like it may have been a little blurry. If it was, I may record something with an actual protractor later on. Okay, but hopefully that gives you kind of a nice feel. Alright, so now choose the number based on whether the angle is obtuse or acute. And we talked about that. Alright? Now, I've talked about one set of angle and measuring it. Okay, I've talked about the different types of angles, acute, right, obtuse, and straight. And now what happens when you have more than one angle? What if you have special pairs of angles? Okay, so now I got a special pair of angles. What if you got complementary angles or two angles whose sum is 90 degrees? So this is the definition, of course, of a complementary angle. So complementary angle is sums to 90 degrees. Okay? So the complement of 70 degrees is 20 degrees because 90 minus 70 is 20. 70 plus 20 gives you 90 degrees. Okay? The supplementary angle are the two angles whose sum is 180. So supplementary angles, the sum is 180. Okay? Now this is how I remember them, right? C, and I'm gonna scooch over here, right? C comes before S in the alphabet, and 90 comes before 180 on the number line, right? So I'm going this way in alphabetical order, I'm going this way on the number line, and that's how I keep them straight, and that makes me happy. Okay, so a complement is 90, and supplementary is 180. Alright, just a little bit. Ooh, not just a little bit, sorry. Okay, so example 2, angle measurements and their complements. Alright, so I've got AB is a ray, and then BD is a ray, BC is a ray. They all share the common vertex of B. It tells us that angle, the measure of angle, and that little m there means measure. So the measure of angle ABC, the measure of angle ABD, because remember the vertex is in the center, right, is 62 degrees. and we're looking for the measure of angle DBC. All right, this is what we're trying to find. And we'll notice that the measure of angle ABC looks to be 90 degrees. Now this little box right here tells us that it's actually 90 degrees, so that's a 90-degree angle. Alright, so the measure of DBC is going to be complementary to 62 degrees. And so if you subtract that, right, if you go ahead and go off, you get 8, right, 28 degrees. And that makes us happy. So 62 and 28 are complementary angles, so they're going to come together to form this right angle right here. Alright? Now, while this one is very straightforward, this is what we do. We use the properties of the angles. Its acuteness, its right angle being parallel. We use those things to help us construct sort of a formula that helps us solve for the unknowns. And these just get a little more complicated as we go along, but it still is basically the same principle, right? Alright, so example number 3. Alright, so the measure of ABD is 66 degrees greater than the measure of DBC, and they are supplementary angles. So what that tells you is this is a straight line, right? Because they're supplementary angles, and ABD is 66 degrees greater than DBC. So DBC is this angle right here where B is the vertex. Alright, and so I don't know what that angle measure is, but I'm going to call it theta, because that's what we call it in math. Alright, and then you have ABD. So ABD is this angle right here. Okay, and it's 66 degrees greater than, well, that's an addition, than the measure of DBC. Well, I don't know what DBC is, but I called it theta. So this is going to be 66 degrees greater than theta. And they are supplementary angles. So I know that these two angles added together, the measure of angle ABD, right, and the measure of angle DBC have to equal 180 degrees. Well, this guy right here, the ABD, is theta plus 66, and the other guy, DBC, is the theta. And so now all I need to do is combine like terms. 2 theta plus 66 is equal to 180. Now I don't know what level you're watching at right here, but of course the theta is the same here and here, and so basically I just combine like terms. Okay, and so 1 theta plus 1 theta gives me 2 thetas. Now I need to, I'm going to give myself a little bit more space, subtract 66 from both sides to get the variable more isolated. Let's see, borrow for 114, which is even, which is nice because now I'm going to divide by 2 because I'm undoing my multiplication with a division. And so 2 over 2 is 1, so I'm left with 1 theta is equal to half of 114 is 57 degrees. So this one is equal to 57 degrees. Okay. The other one is equal to 57 plus 66. And those are the two supplementary angles for this particular problem. Alright? So again, you know, I just took the fact that I knew what supplementary were, translated this using some of my algebra, and worked out a solution. So this chapter, as you can notice, is about the only place that we've been using any real algebra. Alright? This is super helpful, okay? Vertical angles will make your life so much easier. So you really want to understand this. When two lines intersect, the opposite angles formed are called vertical angles. Vertical angles are always equal. Always, 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 always equal. So if this guy right here is 68 degrees, then angle measure number 1 is its right angle, and that's also going to be 68 degrees because they're always equal to one another. Okay? So vertical angles here equal to each other. Now, it does tell you that it's two lines that intersect, right? So you can look. This is a line, and so this line has 180 degrees in it. I'm going to call it line L. And so, of course, L is 180 degrees. Okay? So, therefore, the 68 degrees over here plus the measure of angle 2 over here have to be equal to 180. They're supplementary angles. And so if I know that one of them is 68 and they sum to 180, I can go ahead and subtract 68 from both sides. And then the measure of angle 2 is going to be equal to 112 degrees. So therefore, the angle of 2, the measure of angle 2, the measure of angle 2 is going to be equal to 112 degrees. I just keep hearing Keith Devlin in the background saying that my notation is getting sloppy there. Now, if the angle measure 2 is 112 degrees, then what you should notice is that 2 and 3 are also vertical angles. They're across from each other. And so that means the measure of angle 3 is also 112 degrees. And of course that makes sense because this line right here, let's call it M, okay? Line M is a straight angle, all right, that makes a straight angle with 2 and 1, okay? And so, or the other side of L is 1 and 3. So all of these have this very tight relationship here, okay, where they all have to add up to 180 degrees. Now, we've started intersecting lines, but we haven't, and the angles that they form. And so one of the most important types of special line relationships are parallel lines, okay? So we just had any two lines, now we're getting special line relationships. And so with parallel lines, lines that lie in the same plane and have no points in common are parallel. They never intersect. Okay, this is just a fancy way of saying never intersect. Now, parallel lines never intersect in Euclidean geometry, which is all we're concerned about. But there are a couple of other types of geometry, and the parallel lines do intersect at some point, but they're curvilinear spaces. If you don't understand what I'm saying, don't worry about it. If you do, you're going to see it at some point. Alright. Intersecting lines, two lines that are not parallel and have a single point in common. So intersecting lines have a single point in common. And then a transversal is a special type of line. I'm going to scoot this up. Transversal is a special type of line that intersects two parallel lines. So this is my transversal of my parallel lines here. Now you're going to notice something very interesting, right? With the transversal, okay? It creates a whole bunch of what? It creates a whole bunch of vertical angles. 1 and 4 are vertical angles. 2 and 3 are vertical angles. In the same way, 5 and 8 are vertical angles, and 6 and 7 are vertical angles. Now I want you to notice that 1 and 3 are also supplementary. Okay? And so 1 and 3 therefore have a relationship, as do 2 and 4. They're supplementary. Okay? Now I want you to understand these parallel lines. Okay? If I were to actually take this parallel line right here and move it down, it would be in the exact same spot with the exact same angle here as I have right here. Can you see that? Can you mentally move this piece, right, and slide it down until it matches up with the 5 right there. And then you go, wait a minute. If the measure of angle 1 is equal to the measure of angle 5, then because 5 is equal to 8 and 4 is equal to 1, that means that also the measure of angle 4 is equal to both of them, and the measure of angle 8 is equal to both of them. And that's true. The same logic will give you 2, 3, and 6 and 7. So the measure of angle 2, the measure of angle 3, the measure of angle 6, the measure of angle 7 are all going to be equal to. There's a huge amount of relationship here because the parallel lines, all right, intersect the transversal at the same angle. All right, so you get all of these relationships that are going on in here. So what do they do with all these relationships? Well, basically they give them some special name. Okay? So here we go. Special name. Names of angles. Alternate interior angles. Hopefully this totally makes sense. I'm going to zoom in just a little bit, right, for this. Okay? So here's our alternate interior angles, right? And the idea is that they alternate sides of the transversal and they're interior to the parallel lines. That's why they're called alternate interior. Then you have your alternate exterior. They're on alternate sides of the transversal and they're to the exterior of the parallel line. And then you have all of the corresponding angles, and the corresponding angles are on the same side of the transversal and the same side, top side of the parallel line, bottom side of the parallel line. Okay, and so you have alternate interior, alternate exterior, and corresponding angles. And in math, we just name stuff like it is. So an alternate interior angle is alternate sides of the transversal and inside the parallel lines, and similar naming convention for the rest of them. Okay? It's a lot of slides. It's a lot of memorization and stuff. I have to zoom back out. I'm playing around with a new camera. I don't. Those of you who are subscribed to my channel, you probably realize I'm just experimenting to try for something good. But here we go. All right. We're just trying to find an angle measure when parallel lines are intersected by a transversal. Well, I know that a whole bunch of these from my last slide are already equal. All right, so I know that measure 8 and measure 5 are going to be equal. All right, and I know that because they are corresponding angles. And then of course I know that 1 and 2 are vertical angles, and so they're going to be the exact same also. So this gives me 1, 2, 3, 4 of the angle measures already. Well, and these guys right here, these are all going to be the same also. All I need to do is use the fact that 6 and 8 are supplementary and take 180 degrees minus 35 degrees, and I should get, let's see, 5, I've borrowed 7, 4, 145 degrees. Alright, so over here, the measure of angle 6 is going to be 145 degrees, which means that because 7 is vertical to it, the measure of angle 7 is also going to be 145 degrees. I'm going to slide this up just a little bit, and so that means that the measures of 3 and 4 are also going to be 145 degrees. They have to be, right? 5 is 35 degrees, and 35 is supplementary to 180 with an angle of 145. And this is a straight angle, so obviously 4 is 145. But this is a straight line too. This is a straight angle, so 5 is going to be supplementary to 3. So obviously 3 is going to be 145 degrees. And of course 7 is vertical to 6, which I found was 145 degrees, so it's going to be 145 degrees. So when you have parallel lines, bisected by a transversal like this, okay, you're only going to have two sets of angle measures, and they're going to be supplementary to each other. And that's kind of the moral of the story, and that makes us happy.